Okay, so section 7.2 is going to be about some transformations, and we're going to do some different ways of solving some of these problems. So I'm just going to kind of go through a couple of them here. We'll do a couple of easier ones to kind of see where we're at, and then we'll kind of just work our way back from there and do some that are a little trickier, for instance, perhaps. So a couple nice easy ones. We're going to take this guy here, plus 7x prime plus 6x equals 3 cosine 2t, and we're going to say x of 0 is 4, and we're going to say x prime of 0 is -2. Just made those up. Don't question where they came from. And so when we're doing these guys, what you need to know is these are the big deals here, okay? So this in general is always true. The Laplace transform of f, the nth derivative of f of t, is equal to Sn, s to the n, times the Laplace transform of f of t, right? And then minus s to the n minus 1 times f of 0 minus Sn minus 2, f prime of 0, okay, out as far as you need to go, out until you get to Fn minus 1 of 0. Yes. That's the n minus 1 derivative. Okay? And so on and so on and so on. Okay? Now, what does that mean for me primarily? It means this primarily for us because we're mostly going to be doing second orders. So it looks like this. It'll end up being s f of s minus s. So now it's the second order, correct? So it's going to be 2 minus 1, so just s to the first, right? And then f of 0, or so big, so it's little f of 0. It's little f of 0, which is where? Right here, for instance. And then minus, and then 2 minus 2 is 0. S to the 0, of course, 1, and so then it's going to be minus the first derivative at 0. Okay? And for the second derivative, this would be s squared, right? And then for the Laplace transform of f prime, like that. Okay, so pretty straightforward. Basically, what you just add each time you take another derivative, you just add one onto this guy. Goes up. You add an s here, and then you add another initial condition on there, of course. This s to the first power, in case you're wondering. Just make sure we're clear on that. Okay, now specifically, people always get confused because they're like, "Oh, it's f of t." So what we're going to be doing up here on this fella, we're going to be using our f of t is really x of t, yes? And so allow me to demonstrate. Okay, so on this first problem, I'm going to be very specific about what I'm doing. Notice it's x of s, not x of t, minus 4 times s, and then it's minus a minus 2, so plus 2, plus 7, this is the second derivative right here, times, it's going to be s, x of s minus 4, plus 6, x of s, and then we're home free. Okay? Now, that is a big deal. Okay, now on this other side, well, we'll take it, so it's going to be 3, and then it's going to be s over s squared plus 4. That is cosine of 2t. Okay? Now, the idea here is when we're going to solve this, we're going to solve for x of s in just a minute. That's the whole plan. We're going to x of s is equal to a bunch of s's and numbers. And then we're going to then take the inverse Laplace transform of that, and we're going to get back to x of t, which is what we're interested in solving for. That's how the game is played every single time. So let's see what we get. Now, on this first problem, I'm going to continue with the x of s routine. After this one, I'm not going to do that anymore because it just gets too gross. And I have a really hard time paying attention because it confuses me. All right, now let's get our x of s's together. How many do I have? OMG gosh, I have s squared plus 7s plus 6 of them. Jay, will it always be the same as this? You better believe it, pal. Every single time. And so it's equal to 3s over s squared plus 4. And then notice we're going to add 4s to this side. And we're going to, all right, now we have minus 26. We're going to add 26 as well. You with me? And then to solve for this fella, you simply divide this entire shebang by this. Okay? And I am left with x of s is equal to that. Now, if this was 1989, 90 or something, when I was a kid and young and what have you, we would do this the hard way. But we're not going to do this the hard way. It just isn't something I believe in. So I usually use z for my s's. It's easier to get to than the actual s key. Oh, shoot darn. No, come back. And there we have it, friends. Let me write that down. So we have 3z. Get up there, you hippie. Stop it. So 3s over 100 s squared plus 4 plus 21 over 50 s squared plus 4 and then you're going to get uh-oh, there's a small problem. Do you see that? I see my problem. You probably saw it down here, didn't you? I forgot my plus 26. Didn't you see that? Dang it. That pisses me off. Well, that part didn't change. Okay, good. Yeah, and 31 over 100 minus 31 over 100 z plus 6. And 107 over 25 z plus 1. Is that right? That's right. Okay, cool. Now, if you take the inverse Laplace transform of this right here, that's cosine of 2t. So this is 0.03 cosine of 2t. This is plus 0.42. Well, no, it's not either, because just a minute, friend. Just a minute. There needs to be a k on top, right? K is 2. So if I put a 2 on the top, I got to divide by 2, so it's going to be 21 over 25, which is, what is that? 88, 84, 0.84 sine of 2t. And then minus 0.31. And now remember, this is e to the minus 0.6 or e to the minus 6t plus well 4.28, I think. E to the minus t. I believe so. Now look what happens at 0. Does this work? I don't know. Let's find out. If you throw 0 into this guy, you're going to get 0.03. Minus that's going to be negative 0.28. Plus that's going to be 4. Boom! This feels good to me, friends. I'm going to go ahead and go to Desmos and just graph it just for a good time anyways. I'm going to go there and I'm just going to hit graph, and I'm going to type in 0.03 cosine of 2x plus 0.84 sine 2x minus 0.31 go away, I hate you, e of let's say 4.28. God, piece of crap. Yay, look at that. Look at that. Goes through 4. Huh? Oh, wait. Did I make a boo-boo? Did I make a boo-boo? Oh, I forgot a plus sign right there. My bad. Does it go through 4? It sure does. Could I graph the equation y equals no, negative 2x plus 4. And what would I say my slope was? I must have said it was more steeper than that, and I wasn't paying attention. Nope, negative 2. Oops. So, what the heck is happening here? 2x plus 4. Something a little screwy there. Good, let's check this out. Let's check it out. Alright, let me see what I did wrong. Okay, well, I found out what I did wrong. It was on the sine function there. When I added that 2 divided by 2, I put the 2 on top, I had to put a 2 on the bottom. It makes the bottom bigger instead of making the top bigger. I was kind of stupid on my part. So I need to put a 2 here, and then this then goes together, and you get to put a 2 here. So it's 21 out of 100, 0.21. I just made it too big. That's our problem. Now, you may recall in the first section, again, we talked about this is very similar to our r. This factor is r plus 6, r minus 1, or r plus 1 rather. And that is why we get our complementary solution is this piece right here. No one is shocked by that. This piece here, well, how are you going to get that? We're going to get that from having a cosine and a sine, which is exactly what I have going on over here. Nice. And so the two pieces will come together. And not just any cosine and sine, be cosine and sines of 2t, obviously, because that's the rate at which we're oscillating. It's not going to automatically change and become something different. Okay, let's do another. Oh, goodness. Say. Cool. E to the negative t. So x of 0 is 4, I guess, again, because I'm a boring person. Looks like we got ourselves a maximum or a minimum here, it looks like, pretty obviously. So this is going to be s squared x of s minus s times 4, or 4s if you prefer, which I do. And then minus 0, so nothing. So then plus 4 times, it's s, x of s, minus 4, plus 4x of s, and then this is going to equal 7 over s plus 1. So if you collect your x of s's together, you will find you have s squared plus 4s of them, and then plus 4 of them. And then on the other side, I will have 7 over s plus 1. Okay, I'm going to, with 4s here, I'm going to add that to the other side. Okay, I have a minus 16, I'm going to add that to the other side. And then I will divide the whole shooting match by this guy. Okay, now I already know what's supposed to happen here. I mean, it's pretty clear. I'm going to have, when I'm all said and done, I'm going to have an e to the negative t, duh, with some constant in front of it. I'm going to have a, if you look at this thing right here, that's s plus 2 and s plus 2. Oh, wait a minute. When that happens, didn't we have something that looked like this? We mentioned it when we first started on these guys. That's right. That's exactly what we're going to have. And this is exactly what the outcome will be momentarily. Okay? We already knew that going in. What we don't know is the coefficients. This little business here I'm doing with the Laplace is doing nothing for me in terms of telling me what I'm supposed to know. I already know what it's going to look like. What I don't know is what the coefficients are going to be. So I'm going to do parentheses. Oops, no, I'm not. I'm going to do 7 divide by parentheses z plus 1 plus 4z plus 16 divide by z squared plus 4z plus 4. And you get that. Well, what do you know, friends? That right there is e to the negative 2. So it's negative 3 e to the negative 2t. This deal squared here is what you get when you get t over, if you recall. That's back on page. They gave us a list of these dudes back on page. What page is that on, Jay? Well, piddly diddly. Thought it was back here. Let's take a moment, shall we? What is the Laplace transform of T e to the at, let's say? I don't know. But I feel like it would be the integral from 0 to infinity of T e to the at times e to the minus st dt. And I feel like if one were to do this, one would do the following. And I'd pull the negative out front, and I would have I'd pull the negative t out front, actually. No, I wouldn't. I'd pull the negative t out front, I guess. No, would I? Yes, negative t out front, and I'd write it as s minus a. And then I'd probably use my calculator to speed the process up. I was still going to finish it by hand, but it's really hard to do this, I think. It doesn't really matter. You with me on that? Don't worry about that part of it, because I'm really only interested in what happens with my t's. Okay, there they are. Now look at that thing. What happens at infinity? Okay, well, before I write that down, I'm going to write this out. I'm going to write this as t over x minus c. So t over, that's going to be a minus s. So that's going to be, right? And then 1 over a minus z squared. And then e to the negative t s minus a again, right? All right? Correct. Now, if we throw infinity into this thing, clearly there's going to be an infinity here, infinity, minus nothing to speak of, you know, some constant, but whatever, still infinity, times 0, yes, because this is going to 0. If you do L'Hopital, this piece wins. It goes to 0 on the upper end. On the lower end, if you throw 0 in here, this piece just goes to 1. This piece goes to 0, and this becomes negative 1 over a minus s squared. So the answer is 1 over a minus s squared, but normally we write that as 1 over s minus a squared. Okay? So what does that tell me? It tells me that the Laplace transform of t e to the at is 1 over s minus a squared. And so if you come back up here and look at it, there it is right there. You see that? So it's t e to the negative 2t. And then it's plus 7 e to the minus t. And I'm done. Okay, and as promised, I knew what it was going to look like when it was started. Before I started, I just didn't know what the coefficients were going to be. That's all. Okay? Now, let's do a couple more here just for a good time. And then we're going to learn something that's kind of a neat deal. Cool. There we go. So, if you have this guy here, f of s is equal to 3 over s plus 5. Okay. I'm going to show you how to do this our old school method, all right? Not just expand, but here it is. Really, what I'm going to do is I'm going to use partial fractions on this guy. So if you multiply by that common denominator, you will get 3 equals 3s plus 5 plus bs. Okay. What does that say? 3, that should be a. There you go. Okay. So think about that. What happens here if you plug in, if you were to do this, if you plug in 0, this goes away. This is 5a, so a is 5/3. Or 3/5 rather. And if you plug in -5, which is the other 0, this piece cancels out and you get -5, so then b would be -3/5. Cool. So what does that mean? It means you have 3/5 times 1 over s minus 3/5 times 1 over s plus 5. If you do the inverse Laplace on those, that's 3/5. That's it, because the inverse Laplace of this is 1. Okay. And then minus 3/5. And then this is e to the -5t. And you're done. Okay. Pretty fun, pretty cool. Kind of interesting in that regard, I think. But yeah, there you go. Nice. So they give you some theorems in this chapter. We're going to run through them real quick and kind of see where you go. So Theorem One is the derivatives, or the Laplace transform for a derivative. Okay. We already talked about that, and then the higher derivatives. Okay. Theorem 2 is one that at first blush you're like, when will I ever use this? Soon, friend, very soon. So the Laplace transform of the integral from 0 to t of f of tau d tau is equal to 1 over s Laplace transform of f of t. So in other words, f of s over s. Okay? And then, of course, if you take the inverse Laplace of this, you will get exactly where you think you should get back to. Now, this is one that, in my mind, I never really saw the point of this one until, well, there's several ways, I guess. That's not true. There's several things that you could think about in this guy. But that's one in my mind. When I looked at it, I was like, well, you know, there's a couple things you could do, and we'll kind of run through them a couple different ways. But the one that shows up the most often for this is, and I'm going to go ahead and show it to you, is in the case of when we get to RLC circuits. Okay, and so as you well know, V equals IR, right? And so it's all about, so then L I prime, and yeah, and then it's the charge 1 over the capacitance times the charge, right? Those are all different ways of saying voltage. Okay. Now, what a guy could do is take the derivative of both sides. Boom, 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 boom. The change in charge is by definition the current. And we're in business. And you'd be like, oh yeah, this is awesome, Jay. I got this. And I know, you totally got this. Minus whatever your initial, now be careful, here's the problem, see? I naught is 2. And you're like, cool, 2s. Oh, crap. This original problem up here, the original problem was a first order. First orders only need how many initial conditions? 1. Oh, crap. Then we can't solve it this way. That's right. You're right. We can't solve it this way. But allow me to demonstrate. Allow me to demonstrate. Q, by definition, is the integral of this fellow. Yes? Yeah? Am I right? So then I could rewrite this as Li prime plus IR plus 1 over C. And I'll just leave it like this for right now, okay? I'm not going to get all concerned about it. Okay? I can use the Laplace transform for a single derivative. I know how to do that, and I have what I need, which is 1 initial condition. This I'm golden on, and then this I can simply replace with I of s over s, that piece of it right there. And now we're home free. That is where we'll use it a ton. A ton. By the way, this is the initial current. What is the initial change in current? Wait, how am I going to... More importantly, how am I going to measure that? Yeah, I don't know either. Okay, it's kind of gross. And so just be aware of that there are some that get really gross. Okay, really gross. Just saying. Okay, so you're like, well, is there any other uses for that? Yeah, there sure is. Let me do another one here real quick. I'm going to do this guy, and you're going to be like, wait, you already did it? I know. I'm going to do it a different way. Okay, so as you recall, we said that the inverse Laplace of f of s over s, right? We said that that is equal to the integral from 0 to t of f of tau d tau. You're like, I don't really get that, Jay. Bear with me. If you look at this as the 1 over s part, this guy right here, you with me? That means that this is my f of s. Are you with me? Now, in your mind, what is that the antiderivative? What is that the Laplace transform of? It's e to the minus 5 tau, because that's what we're using right now, d tau, from 0 to t. So let's do the antiderivative. That's going to be negative 1/5 e to the minus 5 tau from 0 to t. If you plug t into there, it's quite obvious you're going to get what? You're going to get t negative t over 5. No, you're not, you idiot. You're going to get negative 1/5 e to the minus 5t minus, and at the bottom, this is going to be 0. So e to the 0 is 1, so minus a minus 1/5, so plus 1/5. I can't remember what I had for that problem a minute ago. Is that what I had? Oh, I had 3/5. Why is there a 3 on this problem? Am I left off somewhere? Oh, you big dope. What a big dope. What about your 3, stupid? It's a good question. Why didn't anybody catch me on that? 3, 3, 3. Same answer. Holy mackerel. I'm an idiot. Let's do another one of those. They're kind of fun. Sometimes. Sometimes they're not fun, though. To be quite honest with you, they're not pleasant, and I don't know that I care. So let's do maybe that one, I guess. Okay, if we're doing this one here, let's break it. Let's forget about this s for a second, because that's quite clear. We could look at this as 2s plus 1 over s squared plus 9 all over s, right? So that's going to go away in a few minutes. Okay, but let's look at this. This could be broken up as 2s over s squared plus 9 plus 1 over s squared plus 9. This is 2 cosine 3 tau. This, I need to put a 3 up here and then a 3 down here. This is cosine, a sine of 3t. So that's 1/3. Okay. So, and that's tau. Okay, so let's take the antiderivative of this, shall we? So it's going to be 2/3 sine 3t, I think, and then plus, no, minus 1/9 cosine 3t. And then if you plug in the 0, or if you I'm sorry, those are the values. That's taus. Sorry, those are taus. I was doing the substitution in my head. I shouldn't have done that. Those are still taus. Tau. So it's 2/3 sine 3t minus 1/9 cosine of 3t. And you throw zeros into that thing, you're going to get 0. And you get 0, and then it's going to be minus 1/9. So it should be 2/3 sine 3t minus 1/9 cosine 3t plus 1/9. Yeah, you're like, I know what you're thinking. You're thinking, well, Jay, am I right? Is this correct? I don't know. Let's find out. What would the Laplace transform of this be? It'd be 2/3. It'd be 3 over s squared plus 9. This would be s over s squared plus 9 plus 1/9. Okay, oops, 1/9, dummy. If I were to get a common denominator, I need to times this guy by 3, top and bottom. I need to times this guy by s squared plus 9. So you'd end up with 6 times 3 is 18 minus s plus s squared plus 9 over 9s squared plus 9. Let's see if that cleans up. It's going to be s squared minus s plus 27. Okay, I'm going to pause for a sec. I need to do some algebra. Alright, sorry about that. The Laplace transform of 1 over 9 is 1 over 9s. Which means my common denominators are all wrong. So let's try that again. See if I can try to not screw it up this time, shall we? Okay, so definitely need a 3 and a 3 and a 3, and I also need an s and an s. This guy needs an s and an s. This guy needs an s squared plus 9s squared plus 9. Judas Priest would help if I could do algebra. The neighbors are being especially annoying tonight. It's 9 times 2 is 18s minus s squared plus s squared plus 9. Still a little stuck here. Oh, these cancel. No, I'm not stuck. Those cancel out, you moron. So it's 18s minus 9 over 9s. Judas Priest, I'm an idiot. There we go. Cool. Lose a 9. You can get 2s minus 1 over s squared plus 9. Are we done? Yeah! We are done. Okay? And it shouldn't have taken that long if I wasn't so dumb. Okay? We'll try another one then. Just for a good time, I guess. If that makes you happy, I guess it would make me happy as well. Let's try it just for fun, huh? Yeah. Why not? Let's do her. So f of s is 1 over s plus 1, s plus 2. Okay, we already know what these are going to be. Again, there's our 1 over s. That piece is going to cancel out. So this is e to the negative t plus e to the negative 2t, right? I mean, that's the game, right? Okay, so what we're going to do is we're going to integrate those guys. Oh, that's a t. Okay, and that in theory should be correct. Let's see if that works. Okay, what is the Laplace transform of this guy? It's this minus 2 s plus 2 plus 2 over s. I really don't want to do this, but because I'm a good guy and all, good grief, that's not true. S plus 1, S plus 2, S plus 1, S plus 2. I should be able to show that it's the same. So on top, you're going to have s squared plus 2s. Then you're going to have minus 2s squared minus 2s. And then you're going to have plus 2s squared. You have plus 3s, so plus 6s plus 4 all over s, s plus 1, s plus 2. All right, let's lose some s squareds. I don't know what you're supposed to end up with. We're supposed to end up with that. Which means that I screwed the pooch somewhere here. Let's see what I do wrong now. S squared plus 2s. Alright, so that's 2s times s is 2s squared. Minus 2s, that's true. Alright, somewhere I screwed up. Just a minute while I fix my... Whenever I check myself I just use a calculator to do it because I find it to be easier. So 1 over z plus 1 plus minus 2 divided by z plus 2 plus 2 divided by z. If you do that, yeah, that's great. Like, well, how's that help? Then you can just go expand. Oops. Oh, not expand, you moron. Just a minute. Sorry. It's not the word I wanted to use. Come on. Expand. Where's the stupid... Just a minute. Pardon me. Okay, I'm getting a little frustrated, so I'm going to do it the hard way first and see if we can get our right answer, okay? So we're going to have 1 over s, s plus 1, s plus 2. Okay, I'm just going to do it this way because it makes me happier sometimes. Right? Right. So A plus B plus C has to equal 0 because there are no s squareds. The s's are 3a plus 2b plus c has to equal 0. And then finally 2a has to equal 1, which means a is a half. Which means that if I do this, I'm going to get b plus c is negative a half. And then I'm going to get 2b plus c is equal to negative 3 halves. If you add here, these guys can't, or subtract rather. If you subtract, let's go 2b minus b is 1b, c minus c is 0. Negative 3 halves minus a half would be negative 2 halves, which would be negative 1. And so I guess that means that c must be a half. Correct? C is a half. C is a half. That's right. So let's plug it in. So a is negative. So a is 1/2. So 1/2, 1 over s. Okay. And then we're going to have minus 1 times 1 over s plus 1. and then you're going to have plus a half 1 over s plus 2. Inverse Laplace of this is simply a half. Inverse Laplace of this is minus e to the minus t plus, and this is a half e to the minus 2t, which I think is what I had the first time I did it, isn't it? That is not the right one. Well, originally that's what I had. I had a 2 here though, didn't I? So there's still a bit of an issue there somewhere. And I think part of my issue was right here. Part of my issue was right here initially anyways, because it should have been minus a half. Somewhere I'm dropping a sign there. I'm dropping a sign there somewhere. So, yeah. So, turns out this is the correct answer. That's the correct answer. Now, I'll see if I can integrate the other stupid thing right this time. Okay, so the whole problem again was up here was 1 over s, s plus 1, 1 over s, s plus 1, s plus 2. Good night, nurse. So it's going to be the integral from 0 to t of, that's e to the negative tau plus e to the negative 2 tau d tau from, yeah, there you go. Somewhere I'm screwing something up, and I'm not pleased with myself. E to the negative x plus e to the negative 2x three halves. 3 halves, friends. So either I can't do algebra, which is very likely, or something else is a little screwy here. So I did calculus right twice. Let's check out my algebra up here. Maybe I screwed something up here somewhere. I don't know. That's correct. That means that C has to be a half to give you negative 1. So negative 2 plus a half is negative 1.5. That's correct. But what about the A? What about the A? What about it, sir? Well, 2A equals 1. A is a half. This is a mystery. I'm going to find it. All right, so here's part of the issue with that one is I think I have to, well, okay, so in reality, I would never do it that way, so that's part of my issue. I would never, unless it was a very easy one, I would never use the integral method for those. I would much rather do it this way, and I'm going to show you this one again because it's so much easier. I think it's easier even if you just do partial fractions personally, but partial fractions on the calculator is obviously even easier here, so that's what I'm doing. Parentheses, z. Oh yeah, close your parentheses one more time. There you go, dummy. So there it is. So clearly you could see it's a half e to the negative 2 t, and then you're going to get minus 1 e to the negative t, and then you're going to get plus a half. Now, what I'm doing wrong, I'm not holding my mouth right somehow, but I think, well, I don't think. Okay, first of all, I understand that when you have a situation where, in this case, you had an s plus 1, and an s plus 2, and really we're only considering the s plus 2 pieces of it, s plus 2 and s plus 1 pieces of it. But the idea is they're multiplied by one another, okay? And so there's an actual theorem for that kind of a problem. It's called the Convolution Theorem, and we'll get to that later on. I think it's in the next section, actually. But personally, I would rather just do partial fraction expansion. I just think it's easier. Now, where will I come about using that integral piece? I will use it a ton in Rlc circuits, a ton. So we'll use that trick, but we'll just use it differently. So don't panic that I did it on 1 or 2, but the other one I just couldn't pull it off. I hold my mouth right somehow or another. Really starting to doubt if I have any brains at all there. So just be careful of that. Okay, so that is section 7.2. I'm going to make a different video for the other ones on here that I need to do, which is 7.3 and 7.6 that I haven't done yet. So I'm going to do those now.